Well, I think it's official. We can get started. Welcome back, everyone. So it's a pretty pivotal week. We're just about ready to get into spring break. And also we had our second exam released this morning. But before we get started with the announcements, any questions or comments to start us out? Okay, well, for the second exam, several people have already completed this, so good work on you all for getting working on it early. It's not a long exam, but it's a good one to get going sooner than later, I'd say. These kind of topics are definitely, they're type of topics that have a shelf life. It's more readily available in your mind if you work on it sooner than on Wednesday itself, I'd say. It's a much easier exam. But this is what the front cover looks like if you haven't opened it just yet, and I should go back here. If you haven't found it just yet, it's found right here on the top of the week, right above where the exam two information is, just as a big old PDF file. You can think of this as something you might print out and solve as a real traditional exam, but you can work on it digitally or just the way you work on any homework assignment, essentially. The way you turn it in will be just like another homework assignment. But because it's an exam, I want to emphasize, I do this with homework, but I try to do this with exams, especially. When you email me your exam, I'll always respond so that you know I got it. If I don't respond in like 8 hours or longer, then something's gone awry. Just resend the exam is probably the safest bet. You can also turn in your exam as a hard copy at the front of class at 5:30 on Wednesday if you like. And it's all kind of off to your option how you'd like to submit it. Any questions about the second exam at the moment, folks? Okay, definitely it's kind of a weird one. We were meant to do this one in class, but I felt like it was going to be a bit of a rush to move the review day, then move the exam day, and then try to get them all graded and returned to you before spring break. Sounded completely impossible. So this is our workaround. Hopefully we won't have any more snow days or anything like that to mess up our schedule. Well, are there any other questions or comments, folks, about the second exam? Okay, other things I should have emphasized there is because it's a take-home exam, it's an open exam. It's open notes, it's open book, open calculator, that kind of stuff. And you're welcome to use other resources. So if you have other lecture notes, other books, or other sources online, you can use those. Just be sure to cite any extraneous class notes, and that would be completely fine. For the next thing we're going to work on then will be in chapter 17, and we've made some headway in there, but this one's actually a pretty long chapter. I'd say this one is more likely something we'll finish on Wednesday's class. Currently, we're on example 3. We're about to do a t-distribution. I think that's it for the announcements. Any other questions at all, folks, before we get started? Okay, well, the current chapter 17 does have assignment associated with it. I posted that this morning, but this one's going to be due well across the spring break that we're getting through. So I feel like 27th of March sounds like a pretty long time, but that's just about right with spring break coming around the corner. Chapter 18 is posted early, just in case we just run out of stuff to talk about on Wednesday. That'd be a next chapter that we'll be launching into. So let's jump then into chapter 17. I think we can close this document. And this is where we left off. This was a while ago, so let's refresh our minds on what is going on here. In this particular study, we have 20 measurements, and these are rainfall in acre feet for clouds that were randomly selected and seeded with silver nitrate. We want to understand how well does seeding with silver nitrate do? And they gave us a benchmark. They asked us the question, does the data provide evidence that the mean rainfall from seeded clouds exceeds 25 acre feet? I wrote down here for the practical question, does seeding clouds with silver nitrate increase rainfall on average? I feel like after reading this again, let's pull this in and say increase rainfall on average. I'll put this in green just to show a change by more than 25 acre feet. So that's a question we'll try to resolve. And you could do this as an honest hypothesis test. That'd be fine as well. But if you want to get more information, confidence interval is sometimes nice because it's going to answer that question as well through hypothesis testing, as well as provide the estimate for the actual rainfall in acre feet. So we're doing this one as a confidence interval. The parameter is indicated to be the true mean amount of rainfall for those clouds seeded with silver nitrate, estimate at 95% confidence. And this is now the fun part where we have to check if the conditions are even met for the statistical procedure we're about to use. Any questions or comments first, folks, before we take a look at condition checking? Okay, this will be our first homework assignment for the upcoming assignment on chapter 17, where we're taking this a little bit more seriously because this is a real honest to goodness professional method in statistics. Sure, it's the first one we might have encountered, but learning how to check those conditions is sometimes even more important than the conclusions you make. You have to know if those conclusions were based on anything. If it was based on sand, we'll find out right away. First thing we have to do is import all of these data. That takes us kind of back to chapter 1 when we were practicing that kind of work. Let me see if I can make this a little bit wider with not too wide. For actually finding the data, just as a reminder, it's all contained in these folders. And you want to download this one right here. Just put it in an available spot. And the steps go, click on this little Excel sheet button, import from text. And for me, it's on a thumb drive. Let's see here. You can leave this exactly like example 3 if you'd like, or you could change it to something that seems to fit the study. We could call this, say, clouds, if you'd like, but that's not super important. As long as everything looks okay down here, then we should be able to move this window down and click on import. So there's our data. I usually click that away, open the data frame, and I'll extract the rainfall data from here. So let's say rain, or just rainfall if you prefer, gets clouds, and select rainfall. Double checking. It's always good to run the syntax to make sure everything's working as intended. But we've got our values in here. It says it's numeric with 20 observations. So the way we'll check our conditions is just through a histogram. Let's hit this right away. Hist for histogram, rainfall for our data. We need to be descriptive, so we need to give a unit for the horizontal axis. The way that goes is X lab for X label. And we could just say this is in acre feet. Or you could be more descriptive and say rainfall for clouds seeded with silver nitrate in acre feet. But as long as you feel enough of what your work already has been written down, let me try to make that sentence. If you feel like you've already indicated what the problem is about in the context with what you've written down here, it would be appropriate to just put down a unit. Everyone's kind of alerted that that's what you're studying. So here's the data, and it doesn't look pretty. If you think back to chapter 1, you have to decide to yourself, is that skewed? Is it severely skewed? Or is it at least roughly symmetric? Those are the major things we were trying to ask back in chapter 1, chapter 2, because it was all about condition checking. That's really the major reason why we bothered about that. So what we'll do is just whatever it looks like, pull in this data. On a real homework assignment, this is part of the explanation of why conditions succeeded or failed. Let me try another screenshot that actually contains the y-axis. One last try. Here we go. Okay, I think we've got it. And finally, there's our data. Any questions at all, folks, with achieving the histogram part? Okay, so again, with these things, you can leave it just as is. We can shrink them down to just fit it if you want to save on printing costs and that kind of stuff. But after we see this histogram, here's what we should say right away. These data are, well, if it has a skew, I'll leave it up to the class. Would you say it's skewed to the left or skewed to the right? I would agree. It looks like because of the heights of these two portions right here, most of the day is constrained in this location and skewing to the left where it kind of trails off, although that's a little off-putting. It sort of had a little jump on this location. But it looks like there is a left skew. Let's say here, the data are somewhat skewed to the left. But the skew on this is not major. It would still be appropriate to say it's roughly symmetric. There's not any major skew to here. So we can say, however, these data are roughly symmetric, with no apparent outlier, we didn't check the 1.5 IQR rule of thumb exactly, but that's not something you should worry about too much unless you can visually see that there's an obvious outlier. At that case, we start to worry a whole lot more. So if there was one extra rectangle in this histogram that was, say, maybe out here, even with just one observation, now we have potential outliers, and that could have been enough to destroy the whole method, depending on the sample size. So everything we say right here, it could be bad. The conditions might not be met if the sample size is really, really low. If this was even more severe skew, if it was tremendously skew, but we have 1,000 observations, that's totally fine. The central limit theorem starts to take over and we get excellent results. So we need to have a benchmark of how much skew is problematic relative to each sample size our study is dealing with. So we'll put down here, since the sample size is n equals 20, and let's leave that blank for just a moment. After looking up the sample size, looking at the situation with the histogram, here's where you'd want to go to this portion of the notes. It's from up above, but we took a screenshot. And just figure out which situation are you in. So we're really looking at this block right here under robustness. What we mean by robustness is the conditions are not met exactly because the data didn't exactly come from a normal distribution. But you can violate that procedure. That's what the robustness is about, to a degree. So we'll see where we're at. Sample size at least 15. We're in this bullet. We're not in this one. This is for larger sample sizes. We're not in this one. This is for small sample sizes. But on this one, it says the t-distributions can be used except in the presence of outliers. So we were very worried about those if we spot them, or if we decide the skew was strong. Here, it's pretty mild. It's appropriate to call it roughly symmetric. So we're meeting that benchmark really well on this particular set of data. So we can say next, since the sample size is 20, the robustness conditions are met. That doesn't mean all of the conditions are met in this study. We have to wonder, how well was this study designed in the first place? Did they actually have random data? Could it be considered a simple random sample? But those are some very, very large questions. You'd have to read the whole study, all of their methods and everything along those lines. For us, this is where we say, briefly discuss if we know our data came from a random sample or not. Let's double check the problem above. They said the clouds were selected at random, so there's a lot of trust involved in this. But if they tell us it was random data, we'll just go along with that. You never have to research this exactly, learn a bunch of meteorology to decide if this was feasible or not. So down below, we can now say, apologies for the page break on the conditions, since the 20 clouds were randomly selected, the conditions are met. Well, you did it, folks. That's the condition checking. And it'll become a common feature for all our statistical problems as we start to move forward chapter through chapter. These conditions start to become familiar. They'll change a little bit here and there. But if we change the type of data, it could change quite a lot. Chapter 18 conditions, however, are actually based on this, even though it's talking about 2 samples. Any questions or comments at all, folks, on running through this part? Okay, let's go to the fun step next and actually carry out the necessary computations as it says. In this class, however, you have some really great options. So one thing you might want to think about is, if your data looks like this, you actually have the raw data available to you. You might as well take advantage of some of the features in RStudio. We did not do this in chapter 14 because the chapter 14 method is not as sound enough for RStudio to have it built in. But this is a very common method. You can do this really rapidly in RStudio. Here's what I would probably do for this situation. Let's go back to RStudio, and I'm going to save the syntax for later. So let's call this condition checking. Now next, we can write t.test. But I know that seems weird. This is a confidence interval hypothesis test that we're doing. But this function is highly overloaded. It has a whole bunch of routines built right inside of it. So we'll do t.test. You have to give it whatever your data was. It was in rainfall. And because it's a confidence interval, you have to tell it the amount of confidence that we want it to be. We chose ourselves that this was a 95% confidence interval. And I'm kind of foggy on that one, but here's the brilliant part about RStudio. If you forget a function, just start typing it out. Confidence goes COL. There it is. That's the right option, and it's usually the top option that's the correct one. Confidence.level is set to 0.95. And even though this is actually the default, I would encourage you to change that and write it in every single time, just in case it's a 99% confidence interval or 90% confidence interval. It's more of a just best practice. It's easy to miss that if we get into a habit of never putting it in. So as soon as you run that, it's done. We did the whole entire procedure, other than the condition checking. RStudio doesn't always help with that. It tells us our test statistic is humongous, but we really don't care about test statistic. We did a confidence interval. It gives us the degrees of freedom. That is relevant to us, but the p-value here is of no consequence. And if you look at this, it says alternative hypothesis, true mean not equal to 0. We didn't set that. That's not even a hypothesis test. So whenever you run t.test, this is pretty common, you have to search for the output that you actually care about. And it's that stuff right there. That is the confidence interval in this whole procedure. Any questions at the moment, folks, in running through t.test? Okay, that's kind of a nice one because you don't have to worry about the null hypothesis, an alternative hypothesis, right tail, left tail test, and all that. You just give it the confidence level. And if you forget any of the syntax, this is always a great place to go. Go back to chapter 17, one sample t procedures. Anytime we get a new statistical method, I post these kind of notes. It's meant to be the one-stop shop for your syntax related to confidence intervals and any syntax related to a left tail test, right tail test, and so on will be always indicated in these kind of documents. But back to our problem, the way I'd probably solve it from here on out is definitely don't copy in all of this stuff. If you want to copy and paste, go to this part of the analysis that's relevant, this right here. So this is all we need. If we just did a confidence interval, we should only give the confidence interval analysis. And if all we were doing is a hypothesis test, then same idea. But some folks might want to put it in their own words. You might just say mu is now greater than 23. Let's round it to say the nearest 10th. So this will be 23.8. It's greater than 28.0, and this is acre feet. So we did it, folks. That's our full-on confidence interval. Any questions at all on getting through that one? Okay, so the next thing we have to do is interpret that thing, but it's really not so bad. Our parameter mu wasn't terribly complicated. Let's look it up just to make it available. We also want to recall what the confidence level was as well, but RStudio tells you that right away as a reminder. And the conclusion can be written out along these lines. We have 95% confidence that, then we go up here and just read out this sentence, that triple site inequality, that the true mean amount of rainfall in acre feet or clouds seeded with silver nitrate okay, got that part, and we'll just say is between 23.8 and, oh, I said 23.8, but I definitely didn't write it. Let me try once more. 23.8 and 28.0. We already mentioned the unit, so we can just end the statement right there. Once we get to this stage, it's always a good idea to take a look at that, go up to the statement we made above, and see if we really answered all of it. I'm not too picky, so if we forgot that part, I don't think I'd take a credit off an assignment. But it was a feature of the problem. You wouldn't want to throw stuff up into the sky that sounds expensive unless there's a benefit. And in the study, that seemed to be the benefit they're going for, that it actually exceeded 25 acre-feet. So coming down here, this becomes a little bit tricky. Would you say we have significant statistical evidence that we exceed 25 acre-feet based off that conclusion? Some say yay, and some might say nay to that. It's honestly kind of a confusing question. Here's a way to visualize it, though. It kind of shows what the problems are, what is easy to miss about this. It's a confidence interval we provided, so everything lives on the real number line as an interval. We're going from 23.8 to 28 in acre-feet, and we have no idea where mu truly is. We just have a certain level of confidence at 95% that mu is really between these two bounds, but it could be anywhere. Let's say it's here, because that's plausible. We'll just draw one document that looks like this. But then 25 acre-feet is here. Now mu can be outside of the interval, far to the left, far to the right. But if it's within the interval, it has a possibility of being below 25 acre-feet. Because of that, we would have to say, and it's almost unfortunate because, I mean, it can get a lot larger, right? We could well exceed it. But if there's a chance that when mu is in your interval, it's equal to 25 or below, we don't have that statistical evidence. And in fact, if we ran a hypothesis test as a two-tailed test, we get the same exact analysis and conclusion. Only thing we get extra here is the actual interval itself by doing the confidence interval. So here we can say, just to end up with that last statement, we do not have significant statistical evidence that the rainfall exceeds 25 acre-feet. So all that for nothing apparently, but at least we have a good analysis and they're making decisions. If this was a real study and that was their real conclusion, they're making these conclusions based off data, not just by a feeling or something like that. But any questions at all, folks, with that full analysis? Okay, it's again kind of a strange way to compute because our studio did all of the heavy lifting for us. We just had to check the conditions, but it makes it kind of tough to learn statistics because you also want to learn about how this interval works, the features of it, and how it all comes together. Our studio just steals all that from us, but there'll be some problems where we're probably going to just do it all by hand. And this would be one of those kinds of examples. Not that you can't force our studio to work out or do a T-dot test procedure with summarized data. I'm sure there's plenty of packages that would do that for you. But this is a good one to do purely by hand because something like this would be a typical exam 3 type of question. I wouldn't ask necessarily a full complete analysis on an exam, I'd say, not an in-class exam. Those are meant to take a little bit more time to get through. So for a real exam, it's usually going to be kind of guided with the parts A through E, like you see down here. Also, we don't have any of the raw data, so we're probably more encouraged as even a homework assignment to do it like an exam question. So let's start off by just reading through the context. What makes it a good exam question is also that it's really brief, so that we don't waste a whole lot of time trying to untangle everything in the context. They tell us the Federal Bureau of Investigation compiles data on robbery and property crimes, publishes the information in population at risk rates and selected crime indicators. Great source of statistics problems if you just get bored and want to Google some of that. We're told a simple random sample of 25 pickpocket offenses in a particular area yielded a sample mean loss of $513.32 and a sample standard deviation loss of $262.23. It's a pretty large standard deviation for this situation. We're probably imagining things like cell phones are being pickpocketed and that kind of stuff in this area. But they told us several things. We have a sample size at 25. From here, because they said sample mean, we know we can indicate this as X bar is 513.32. The sample standard deviation, because it says sample, we can indicate that one as a S equals $262.23. So that's the whole situation with all the information. Now from here, we can do the same kind of analysis, but we'll do this one from scratch. First thing we have to do is decide and describe what is the unknown parameter. Because these data are very quantitative appearing, we'll use mu and say that mu equals the population mean, and we could say amount or mean loss, anything along those lines. Let's say mean loss in dollars. We have to be descriptive, loss due to what cause. This problem is all about pickpocketing offenses, so that should be reflected somewhere here in the parameter mu to also be used in the conclusion. So we'll say the population mean loss in dollars due to pickpocketing It didn't say what area this was in, probably just to protect that area. This one came from a textbook and they probably just didn't want to highlight any weird area. That'd be just kind of mean for any students that were from that place. So it just said in that area or that particular area right here. So we'll just say pickpocketing in this area, wherever it was. Well, we have the parameter down. Next thing we're going to do is just look at all the different moving parts in that one sample t-test and eventually put it all together down here in part D. Any questions first, folks, with what we have so far? Okay, the first big one is this thing. As an exam question, this is more about a concept type question, really. So we have to know once you saw standard error, the major thought is that that's a huge buzzword in statistics. It's typically written this way or abbreviated this way, SC for standard error. If your data is quantitative and there's just one sample, you're really calculating the standard error of X bar. So it'd be written this way, SC X bar. And the formula goes S divided by the square root of the sample size N. It says round to 4 decimal places, but that's kind of just generic advice for this kind of problem. Our S value is $262.23, and we're dividing by square root 25, or just 5 if you simplified that. All we need now is a good calculator, the same one you might bring to an exam, can take care of this whole problem, except for, of course, the critical T-star, but we'll calculate that. So we have 262.23 divided by square root of 25. Let's just put it in a 5 to save a step. And my value came out at 52.446. So the standard error in this problem is 52.4460 if you're following the instructions to the letter, rounded to 4 decimal places. Well, any questions, folks, with the standard error? Okay, really the major thing is just to know when you see standard error, it's indicating this whole formula right here. Then the computation is pretty quick to get through. Next thing we need is the degrees of freedom. Yet another buzzword, so I'll try to highlight those as things to watch out for that's indicating a formula. The formula for this one is DF for degrees of freedom. Anyone see what the degrees of freedom should be in this problem? It's definitely been a while since we looked at that formula. But the good news is, it's a wonderful formula. The bad news is it gets terrible in chapter 18. That's one of the things to watch out for in statistics. When it says degrees of freedom, it's going to be called this, but the formula depends on, do you have one sample or two samples? Chapter 18, this thing gets pretty wild. But here, if it's just one sample, we go n minus 1. So kind of the best formula ever, really. So look up your sample size, it's 25. Reduce it by 1, and the degrees of freedom in this problem are 24. From here on out, this is where the problem would be a terrible exam question, because I do need to give you a T star. So in a real exam question, it'll say, use the fact that T star equals whatever the value is. But for us, this is a good review of how to calculate it from scratch. To get the full interval, let's indicate the formula. It's going to be X bar, add or subtract, T star, multiplied by the standard error of X bar. I think I want that whole thing color coded. Let's just hit it like that. There we go. So it's all about calculating that T star at this point, but it's always the same kind of formula. It goes like this. T star is going to be negative Q T, so quantile for the T distribution. And we need a confidence level. Let's take a look. Oh, it said 95% confidence right here. So we'll take 1 minus 0.95 divide by 2, where the 95% came from that statement of the problem. Next thing we have to give it is the degrees of freedom for the last output. So that'll be 24. And just a quick note, this is the degrees of freedom. So it's always calculated just like that. You'll change your confidence here, change the degrees of freedom, but it's ready to go in that format. Let's see what we get. So down here, we have negative QT, 1 minus 0.95, maybe move that red dot, divide by 2. 24 degrees of freedom gives us that critical number there. That's a 2.0639 would be a good place to round it. So we have pretty much all the loose ends with that critical number here. We'll just plug it in and crank it out. Any questions at all, folks, with the critical number so far? Okay, before I forget though, I noticed that I did not save the syntax. So let me take this and just throw it here for good measure. You think that's easy to remember, but I've really been struggling with that this semester. If you ever notice that syntax is missing in the notes, just email me right away and I'll be very happy to correct the record and put it back on there. Okay, the rest of it is pretty much plug and chug. We'll go back to the interval method right here. I just pull in the information. So this will be equal to, for X bar, right here at the top, it's 513.32. We'll add and subtract that quantity just found, 2.0639, and multiply that by where it says standard error X bar, we just pull in that whole number, 52.446. Last thing to do is just calculate the lower bound, upper bound. I'd like to write my results like this, but you don't have to. You can give it an actual mathematical interval. We could just say lower bound equals, upper bound equals, all pretty much up to you. The major thing is how you give a practical conclusion at the next step. So back to the calculator. I'll start with the minus here and go 513.32 minus 2.0639. I forget this a lot. In RStudio, you need to go star if you're using this as a calculator to multiply 52.4460. It's good to double check these. Let me see, 2.0639. I think we've got it. So enter there, that's our lower bound. This is in dollars, so we can round to the nearest cent, 405.08. Then if you've got it in your calculator once, figure out which shortcut you have in your calculator. Sometimes you hit second and entry to call up the very last computation. If you're using RStudio, use the up arrow. So all you want to do is go here and change that to a plus. But I promise you, if I had to type that out twice, there's a really strong chance I'm going to make a mistake on the second time. I don't know why that is. So any kind of shortcuts you can find in your calculator is great for accuracy. So this comes out as $621.56. So we did it, folks. That's doing the whole confidence interval from scratch. I feel like this part right here, T star, is the trickiest part. The rest of it is exactly the same as chapter 14. But that's the syntax you'd want to use anytime you calculate a T star. You can look up on the notes as well, where we did a couple of these just for the practice. Well, any questions at all, folks, with the intervals so far? Okay, next, we just want to give it a practical interpretation, but always goes kind of the same way. Oh, first we have a question. Oh, QT stands for, that's a really great question. The Q stands for quantile. With the quantile, think of a best analogy would be whenever we're looking at, say, the lower quartile or upper quartile or the median. Those were the kinds of things we were looking for. When this one says quantile, it means we're taking the 0.025% on the left instead of a 25% going to the left, like quartile 1. The T, though, stands for the T distribution, or student's T distribution, if you like. So it's kind of like when we did stuff like, say, Q norm or P norm back in the day, but instead of norm, we just throw in T. So QT and PT are the new functions in chapter 17. Does that make sense for the QT function there, Hannah? You bet. Other questions or comments at the moment? Okay, well, we're ready for a practical interpretation. Our parameter wasn't terrible. It's the mean loss in dollars due to pickpocketing. So we'll just say, let's see, with 95% confidence, the mean amount lost due to pickpocketing in this area is between $405.08 and $621.56. And looks like we did it, folks. I think that's the last part there. Yeah, it is. That's the full procedure. So this is about what an exam question would look like. And there is value in doing questions like these because if you're just given nothing but summary data, now we have to walk through each part of the confidence interval and really dissect it. And that's a great way to really learn it at the same time. Any other questions or comments at all, folks, before we try the next concept? Okay, well, that's how confidence intervals goes if we're doing the T distribution. And hypothesis testing, it's not too different from chapter 14 either. We have to make a couple corrections, but they're the same corrections we made before. Instead of using a sigma divided by root n, we have to use the standard error. So that's our first change. The standard error involves s over root n, and your numerator is completely the same as it was in chapter 14. Whatever the null hypothesis is, we take the hypothesized value and throw it in here. So what T measures is exactly what Z measured, except that that's an approximation of the standard deviation, and that tells us that this is all equal to the approximate number of standard deviations that your data, X bar, is away from the value that's to be tested, the status quo or the value of the null hypothesis, mu naught. If that's a lot of standard deviations, say if the t-test statistic came out as 3 or 5 or something like that, it starts to look like X bar is very far away from the statement here, and so the null hypothesis is going to be rejected. It doesn't even look compatible with the data if that's a large number. And you get your p-values from doing one of these 3 different tests. So your alternative hypothesis has to be specified. This one is always the default, just like in chapter 14. But we look for language that might tell us it's a right tail test, meaning your alternative will have a greater than sign, and same with the left tail test here. The way we calculate p-values changes now because we're not in the z distribution, we're using the t distribution. So my thought this time is, instead of filling out a whole bunch of graphics like we did in chapter 14, it might be better to just do several scenarios. I have a two-tail test, a right tail test, and a left tail test. And we'll make this our location where we figure out how to calculate all those p-values. Does that sound right to folks? Okay, so this can be your place you'd want to come back to if you want to look up calculating p-values. But I also would encourage you, if you're looking up how to calculate p-values, take a look at this document as well, because if you have the sample data, you probably just want to use t.test. If that problem is more about the conclusions that you're making and the conditions that you're checking than the actual computations. But if it's raw data like the one summary data like what we did here, we'll have to calculate those things from scratch. So let's give this a try. On our scenario 1, it says, the one sample t statistic, so they're referring to this thing, for testing a null, mu equals 5 against the two-tail test, mu is not equal to 5, from a sample of 30 observations is negative 2.08. So they gave us a lot of information all about the test and the test statistic. We just have to decide if we're going to reject or fail to reject the null hypothesis. At significance level, 0.05. So first thing to observe is this one is two-tailed, which means that's the underlying formula in a probability statement of what we're using, but that's not the syntax. Our author has no idea what product we're using to calculate these things. For us, we'll go and write that the p-value is going to be, because it's a two-tailed test, we'll multiply by 2 right here. It multiplies, in chapter 14, we would have said p-norm, but because we're using the t distribution, we say pt. It almost looks too simple, but that's the syntax we have to use in this case. Now, next thing to take a look at is the uppercase T is playing the role of that entire t distribution with 29 degrees of freedom, and we want to make it greater than or equal to the absolute value of lowercase t. That would be this one right here. So you'd want to type in ABS for absolute value, negative 2.08. I'll just put a T here just to signify that's where you drop your t test statistic. Because there's a greater than sign, and we didn't put a negative in front of there, you also have to throw in another option, lower dot tail, set false. And that completely specifies what our p-value should be in this situation. Let's double check though and see what we get out of this. So back to RStudio, we need to take 2 times PT. And before I get too far, I did miss one thing. It's a kind of a huge deal as well. If we try to type all this out, there's going to be a big syntax error. Anyone see what thing we missed that should be inside here before lower.tail is false? I shouldn't say we missed. That was definitely me. I missed that one. The weird thing about the t distribution is sample sizes start to matter a whole lot, and it isn't it a standard deviation? It's less about the standard deviation, but it's more about that sample size right there at n equals 30. We have a different t distribution for every single different sample size, and so we have to bring in that information using degrees of freedom. Glad we're doing this problem. It's kind of easy to miss on these things because we never had to do that in chapter 14. But from here, we have to say, let's use a pen that's going to stand out. df is n minus 1, which is 29. And so 29 have to go right here as an input to the pt function. I'll just put here the pencil tool. Degrees of freedom go in that location. Then we can put in lower.tail, set false. So I think we're about ready to do it, folks. That's everything all in the line, including the degrees of freedom. So this should go 2 times probability of the t distribution. I'm throwing in the absolute value just because that's how you might write it if you're developing an entire syntax for this, but if you put positive 2.08, that's fine as well. The next 29 degrees of freedom, lower.tail equals false, and that's the entire syntax. We get a p-value of 0.0465. And now this becomes kind of a review problem in a certain sense. If that's our p-value, and we're dealing with a significance level of 0.05, any volunteers for what the decision should be? Is this rejecting the null hypothesis or failing to reject it? Oh, we got one from Zoom. Aspen says reject. Good call, Aspen. Thanks for the response on that one. If we have something smaller than the 0.05, that's what they were trying to find in the study. We now have evidence for the research question, which is typically encoded as the alternative hypothesis, as having some truth to it. We found evidence in that direction. So what I'd probably write down next is, the moment you calculate a p-value, you want to compare it to whatever this is set at in the problem at a 0.05. Because we said less, we'll say next, we will reject the null hypothesis. So that's our conclusion on this problem. We will reject H0. Well, we did it, folks. That's calculating a p-value in this case. This problem is more about doing the p-value than anything else. But any questions or comments on that first one there? Okay, so the p-value for this one is kind of complicated in a way. The author had to write down one specific formula. He decided to have area to the right, so that's why it looks like this particular format. There are other ways to write this out. So if you like smaller syntax, here's another option. You could write in 2. Let me put it down here, just call this option 2. I think that'll be less confusing. You could write out p-value equals 2, probability, that would be a lowercase p, for the t distribution, and negative absolute value of t, degrees of freedom, and that would actually do the whole job right there. Because if you put a negative, you force your test statistics to now go on the left end of the distribution. There doesn't have to be a statement about lower.tail's fault. We're still doubling the right area. The curve is totally symmetric. This just forces your test statistic to the right, and this one forces it to the left. So I'd say go either option that makes the most sense to you. I usually write out this way because presumably that's the way you probably read about it in the book as well. Well, that's a lot of stuff to talk about for just one p-value, so let's try it out again. Part B says, the one sample t statistic, now for this test, this is a right tail test, came out as a 2.04. But really the most important thing to remark about this is, first thoughts with p-values is, which test is it? And from right there, this one is a right tail test. In a right tail test, the p-value is a lot easier to compute. We're just going to write p-value equals, we don't double anything, that's only for the two-tail test. We just start on this end of the syntax. Probability for the t distribution. We go to the test statistic, and we don't do anything to that either. Whether it's positive or negative is irrelevant. We expect it to be positive, it's a right tail test, but that's not a requirement at all. So just grab whatever that is, 2.04. So that's the whole t-test statistic there. Next, go to the sample size and drop it by 1, so 29. That'll be our degrees of freedom for the second input. And it is a right tail test, so that means all of our p-value area is to the right. And that finally means you need lower dot tail to be set false. So with that syntax, we should be getting a p-value pretty quickly. And take a look at the difference between the magnitudes. The sign is not as important as how big it is away from 0. This p-value is not going to be as large in a certain sense because of that right there. But it's also going to be a lot smaller because you're always doubling your p-value in a two-tailed test. In a certain sense, people like that. It means you're not going to make a type 1 error very often if your p-values are always a lot larger. But if there's a good reason to do a right tail test, if this research question was always about directions towards the right, we shouldn't worry about that. We should just do what the people wanted, that particular test. So let's write that in as PT 2.04, 29, lower dot tail, set false. And that's our next p-value. Notice it is practically a half of this one, and that's more to do with the 2 here being taken off than it is the difference between 2.04 and 2.08 in magnitude. So we had got a 0.0252 or 0.0253 if you like. Now this one is definitely less than 0.05, which is equal to alpha. And so just like in the last problem, because we put a less than right here, we will reject H naught. Well, any questions, folks, with that second level of syntax? Okay, one thing to mention though, because this really happens and it's incredibly unethical, sometimes people have found themselves in this situation where the research question they really want to address was a two-tailed test, but maybe the p-value came out at 0.0513. That's almost tragic in a way, right? Especially if this problem was near and dear to you. You spent 10 years of your life working on it and finally got the data, and it's insignificant. It would have been greater than alpha. We could not reject the null hypothesis. Some people have actually redesigned their test to make it be a right tail test or a single tail test just to drop the p-value. And when they get caught, that's extremely unethical in sciences. That can have all sorts of huge consequences. And it means these studies have to be redone. The data is, or the conclusions were not in the right direction. In a way that's good, we should be redoing these tests to see if we can repeatedly get significant results. That's one thing to worry about when it comes to hypothesis testing. Whatever you said your null was, and your alternative, and your significance level, that's done before you even see the data, and it has to be maintained throughout the entire problem, even if it gives you a conclusion we don't want. Well, let's try out one more time for part C. This one is a left tail test because of the directionality here. And that means calculating this test statistic shouldn't be too bad. Here, if you saw a test statistic at this magnitude, that doesn't look too exciting. It looks like we are probably going to fail to reject the null hypothesis this time. It does depend on the significance level, but this one's still at a 0.05. I didn't change this on any of those. The new thing, however, is, fix that. The sample size is at 100, so this will be pretty similar to calculating on a normal distribution. But despite that, we'll still use PT because that'll give us the most accurate p-value possible. So on this one, it'll be p-value equals PT. Just like with the left tail test and the right tail test, the sign doesn't matter. We just take whatever we found in the problem. If it's negative, we'll throw it in negative. So negative 1.53. If that sample size is at 100, we drop by 1 for 99 degrees of freedom. And that's the whole thing. The syntax gets kind of nice for the left tail test. We just drop in the test statistic and degrees of freedom in those two spots. Okay, so coming down next. Let's suppose we did calculate this using the wrong distribution. We might have made a mistake and just put in p norm. give it that test statistic, negative 1.53. And that's all you would have had to have done in chapter 14. And that's the p-value, 0.06. But that p-value is definitely not accurate. We need to calculate it this way. Let's see just how close our results are. So doing it correctly now, probability with the t-distribution, negative 1.53, 99 degrees of freedoms, gives us, it's pretty similar. But that's what we're expecting. Whenever your sample size is large, the t-distribution starts to look a lot more like the normal distribution. But it's comforting to know that this could make or break a problem. This could have been just enough to be above or below alpha. We should always calculate as accurately as possible. So this one is a 0.0646. This time, that exceeds alpha at 0.05, so we'll go greater than. I want to go greater than or equal to, even though that looks weird, because that's the benchmark when we fail to reject the null hypothesis at equality as well. Although that would be really weird if you got exactly 0.05. It'd be like kind of winning a lottery in a certain sense. Then the next thing we can say is, because of that directionality here, we want the less than, but here we will fail to, let's say it's slightly different. We will fail to reject H naught. Not meaning we found evidence H naught is true. What it means is we failed to find evidence that that was true. That's where the research question is really contained in these kind of problems. But we did, folks. That's 3 different kind of p-values. Any questions or comments at all with getting through these? Okay, well, with all that practice out of the way, let's see how we can get into this very next problem. So example 6 looks like it's something to do with 2 samples right away, and that might already be a concern, because if we're using the methods we're dealing with right now, it's the one sample t test statistic we're calculating. This looks like a major concern, but it's actually not as concerning as it looks. This says patient ID, so this is not the variable, this is the identifier in the problem. The reason it was pulled into these data was we need to emphasize that these data right here, for example, were measured on the same person. The same person was measured twice. Something that happened at 12 hours, something that happened at 10 minutes. But because of this feature right here, we can say these data are dependent, since they are based upon 2 measurements with the same individual. So this is actually really kind of tricky in a certain sense. When we get through chapters 18, 19, 20, and so on, we start to look at data, and it's not always easy to deconstruct it and decide which actual procedure do we really need for this. This one will be, I think, pretty tough to pick out once we have a lot of statistical procedures. But if it's dependent, because there's 2 measurements with the same individual, the actual test you're using has a name. This is going to be called the paired one sample t-test. We're going to use the same exact procedure, but we just have to form the data right. It turns out we don't care about this column completely. Highlight that weird. We don't completely care about this column in isolation. We don't care as much about this column in isolation. We want to know what happens if we subtract the 2 columns from individual to individual. We're using a paired one sample t-test on the differences. That's a good one to include here, on the differences. Deserves an exclamation mark because, again, if these were unpaired data, this is a chapter 18 problem, and all of the methods have to change pretty substantially to make the analysis come out correct. Well, any questions or comments, folks, with the initial look at the data? Still not sure what the context is, but we can tell just from looking at it, these are paired data. That's probably the most important takeaway with this problem right here. Now, here's what actually happened in these data. It's from 1983. This is a while ago. It involved Quadlin, Masteller, and Tukey. Tukey is a massive figure in statistics. They presented data on blood levels of beta endorphin as a function of stress. So here's what they did. They suspect beta endorphins are somehow a function of stress, they say. So they took the beta endorphin levels for 19 patients 12 hours before surgery. Remember, they're trying to measure stress, and you can imagine maybe you're having like a total knee replacement. I'm stressed out 12 hours before surgery. They'll take your beta endorphin levels, and then they're going to do it again 10 minutes before surgery. I thought I was stressed out at 12 hours, but at 10 minutes before, that's like a whole new world, especially if it's a substantial procedure. So if beta endorphin levels has something to do about stress, this seems like a pretty good design to spot that. Let's see if it really something is going on. Let's take a look at these data. Patient number 1 was cool as a cucumber going in and was more calm right before the surgery. So that one's kind of weird. But you can look at other people. I think if I was going to get a surgery, I'd be more like patient number 11. Kind of okay because it's 12 hours out. And then once reality sinks in, I'd be very stressed out. So again, it's not about the baselines or the final amounts. It's about how much did it change. That's why we care about the differences, not each of these original distributions here or here. We care about the paired data, or the differences the most rather. So that's the story behind the data. They ask us, well, they tell us, the data presented are in femtomoles per milliliter, and based on these data, what effect does increased stress have on endorphin levels? So that's the whole question, and we'll provide a complete analysis, this time with a hypothesis test. So that's the walkthrough of the data so far. Any questions at the moment, folks? Okay, they ask us to state the practical question. And again, this is something you can rephrase, something you can cite directly. It looks like it's pretty much right here. I mean, if you see a question mark, that's kind of a dead giveaway. Let's say here, if we're putting in our words, it could be something along these lines. Does stress affect beta endorphin levels on average? I like to say this last statement here, on average. This is a reminder that our analysis isn't about individuals, it'll be about averages and population averages we're thinking about. So that's our practical question. The next portion is tricky whenever we're dealing with paired data. We have to decide, well, if we're dealing with the differences, how should we subtract? Now, if we think these values should be larger, and they really look larger, I didn't see what happened to patient 13. I almost want to give that one a person a hug. That's pretty rough. Looks like it's higher on this column. So it also would make sense to take the 10 minutes and subtract the values from the 12 hours. That's going to be the actual parameter we want to analyze. So when we go to define the unknown parameter, we can say let mu, you could write it as mu if you like, or a subscript with d to emphasize you're dealing with differences. I'll leave that as a stylistic choice up to you. Let's say let mu equal the population mean difference in beta endorphin levels for 12 hours minus 10 minutes before surgery. So that's our parameter that we'll analyze. I usually color code that one, but let's just hit it with blue like that. That'll do the job. Next thing we need are hypotheses. Once we get through this stage right here, the condition checking is not too bad. It's kind of the same as what we did at the start of the class. We have raw data, so we'll use t.test right here. really, this is where most of the fighting is. If we can get this down just right, everything else is easier, especially the conclusions. We're just kind of following our nose there. So it's going to start off like this. H naught. It's relative to the parameter mu we just specified. So mu would go here. We have an alternative hypothesis, still relative to the parameter mu. Our author always puts equality here, but we now need a value, and that's kind of hard to spot. There's a trick to it if you're dealing with differences. Anyone see what the most sensible number would be right here? One way to think about it is usually the null hypothesis is a statement of no effect. It's a statement of the status quo is maintained. It's essentially saying nothing is going on at all. And if nothing is going on, then the difference of the amount of stress at 12 hours should be, well, I shouldn't say the amount of stress, the beta endorphin levels released at 12 hours should be about the same as beta endorphin levels at 10 minutes. The null hypothesis is saying nothing's changed. If that's the same, we would put a 0 here. And I think that's highlight worthy because this is very typical. If you have paired data and you're concerned about differences, something in the problem would have to tell you, and it would have to be explicit, that you're looking for a difference other than 0. Nothing is said, then that's always a really good assumption to make. And it's the right assumption in this problem as well. Does that make sense to folks with what goes right here? Okay, so this is pretty much the norm for a paired one sample t-test. Now, over here, if we put it 0 for the null, we'll also put it over here, so that's kind of helpful. But the last thing is what goes in the middle. Let's use a special color, so we'll try to find the keyword that directs us. We want to know, is that a less than, a greater than, or a not equals right in the middle? Anyone spot which kind of test this should be? Let me take a look. What effect does increase stress levels? Now, right there feels like a greater than, but I think it was actually part of the design of the test. They were looking for someone with stress here, but then an increased stress levels. So that right here is not necessarily indicating a greater than necessarily. Aspen says not equal, and I think that's actually the intent on this. When they said what effect, that meant they were looking for any variation. Maybe beta endorphin levels go up, maybe they go down. They're looking for literally anything when they say what effect right there. That's awfully tricky, I'd say. So standard offer, when you're doing a homework problem, if you have any confusion with setting down mu, or if you're just not sure about your hypotheses, don't hesitate to send me a screenshot of your work, and I'll be very happy to discuss these things, because they are fantastically tricky. And to me, this is the only thing that stands out as a key word that would tell us it looks like it's a two-tailed test. We should be using not equals. So not equals would go right here. Does that make sense to folks on getting that not equal there? Okay, again, that's always extremely tricky. The planning phase for a hypothesis test, it doesn't have a whole lot of extra points. So if you make a mistake, you're not going to get repeatedly dinged on them. But it's frustrating to not get it right. So I'll try to always emphasize, here's where we decided it must have been a two-tailed test. And in all honesty, if this was completely gone, we had no keywords whatsoever, and we're just puzzled on what they wanted, the two-tailed test is the default. So if you're not sure, that's always a great response. Let me try to fix that a little bit better. There we go. Well, we got through the worst of it. Next thing we'll do is some condition checking. We'll run through t.test as a hypothesis test procedure. But you know what? I think we did forget one thing. This is a hypothesis, and they never specified a significance level. So let's make that our last step. We'll test these two hypotheses at alpha equals. It's completely up to you if you decide this problem is particularly interesting and a type 1 error might be problematic. You might go on the low end of 0.01, but you're increasing a type 2 error when you do that, so you have to balance this. If you're not too sure, a 0.05 is just fine as well. So if you feel like a 0.05 is how you'd like to analyze it in the homework, if this is a real homework question, that'd be totally okay. But how about for the sake of fun, let's go for a 0.01 on this one. Is that all right for everyone? Okay, it makes some sense. I mean, this is a study about medical science and what happens with beta endorphin levels. So we're going to put a high level of rigor before we really reject the null hypothesis, meaning type 2 error went up. So always keep that thought in mind. Lowering alpha doesn't make everything wonderful. It's always a balancing act. Well, I think it's a pretty good stopping point for us, folks. The next things we'll do and we'll talk about is when you do check conditions, anything that happens here is totally irrelevant. It could be the worst skewed data you've ever seen with outliers, and same for the data over here. But condition checking has nothing to do with either of those data. Well, it sort of does in a roundabout way. It's about the differences. We have to form all the differences and look at a histogram of those. That's where all the condition checking actually happens. That'll be a good one to come back to on Wednesday's class. Well, have a great night, folks. If you have any questions or issues with the exam, the take home that's going to be due on Wednesday that I'm trying to navigate to, don't hesitate to reach out. I'll be happy to help out. And that's what we'll be working on when we come back on Wednesday, this problem here. Thanks, folks. Have a good one, and I'll see you on Wednesday. One more to go, and we'll be on the break. Me too. This will be a good catch-up kind of break, I think.
That's less exciting.
It's less exciting, but you know, it's kind of like light at the end of the tunnel kind of stuff. Thanks, folks. Yep, have a good one.